right now, if you live in a major city, one that relies on traditional central heating, a massive portion of your monthly heating bill isn't actually going toward warming your home.
No, it really isn't.
You are paying to heat the dirt, the rats, and, the frozen pavement miles away from your building.
It's kind of wild when you put it like that.
It is a century-old, deeply inefficient system, and, most of us don't even realize it's happening. But today, on this deep dive, we are looking at a fascinating set of technical standards titled Constructive Solutions for Autonomous Heat Supply Systems.
Yeah, it's a really eye-opening document.
And what these documents reveal is that engineers are actively, fundamentally dismantling that old model. The giant, impersonal city grids that pump hot water across miles of underground pipes are being replaced.
Completely replaced, yeah.
We are moving toward highly efficient, incredibly localized, and shockingly smart systems that operate right under our noses. So for everyone listening, you're going to want to hear how this changes literally everything about the buildings you live and work in.
It really is a profound shift in civic engineering. For a long, long time, the dominant model was entirely centralized.
Right.
You had one massive power plant burning coal or natural gas, generating enormous amounts of heat and forcefully pushing it out to an entire district.
Just brute forcing it.
Exactly. But the source material we are examining today breaks down a completely different, decentralized approach. We are talking about a transition to autonomous systems.
Which means what exactly in practice?
Well, that includes gas boilers attached directly to the sides of buildings, high-tech automated stations mounted on roofs, block modular containers sitting quietly in courtyards, and even micro-generators installed right inside individual apartments.
Okay, let's unpack this, because the best way I can think to describe this transition is to imagine how you get your food.
Okay, like this.
The old centralized heating model is exactly like standing in a massive, crowded, institutional cafeteria line. Whatever the central kitchen decides to cook up in bulk whenever they decide to serve it is what you get.
Right, and you get it at the temperature they decide.
Exactly, it is blunt force. But this new autonomous heat supply system, it is like having a highly efficient personal chef right in your own kitchen, cooking exactly what you need, exactly when you need it, without wasting a single ounce of energy.
I love that personal chef analogy, actually, because it leads us directly into the ultimate expression of this engineering philosophy. The sources detail this extensively. It's apartment-level heating.
Yeah.
This is the highest possible degree of decentralizing a utility. Instead of relying on a distant plant miles away, or even a boiler down in the basement of your own building, you have a small, wall-mounted gas boiler installed right there in your individual apartment.
Right in the kitchen or bathroom. And according to the specs here, these are those giant roaring iron beasts we picture when we hear the word boiler.
Oh, no, not at all.
These are remarkably small, usually putting out about 24 to 28 kilowatts of power.
Precisely. They are incredibly compact.
But wait, hold on. You're telling me the ultimate engineering solution is to put a machine that literally burns natural gas inside my apartment?
Yes, that's the idea.
In the same space where I sleep. We have spent decades putting smoke alarms and carbon monoxide detectors in our homes to protect us from exactly this kind of thing. How on earth is that safe?
It is a totally valid concern, and it comes down to a crucial design element, which is the closed combustion chamber.
Closed combustion.
Yeah. When you picture a fire, you know it needs oxygen to burn. Old systems, like a fireplace or an old furnace, draw that oxygen directly from the room they are sitting in.
Right. They just pull the air from the basement.
Exactly. And that is where the carbon monoxide risk comes from, because the exhaust can easily mix with your breathing air if there's a draft or a blockage. But these autonomous units are entirely sealed.
Oh.
They use a clever concentric pipe system. Think of a pipe within a pipe.
A pipe within a pipe.
Yeah, so they draw fresh air from the outside through the outer layer of the pipe, feed it into the sealed chamber to create the fire, and then push the exhaust gases right back outside through the inner pipe.
Wow. So the fire is entirely isolated. The air the boiler breathes, I guess, to create the flame never once touches the air you are breathing while cooking dinner.
Exactly. It is physically separated by gas-tight ducts.
Yeah.
And once you understand that safety mechanism, you can really start to appreciate the economics of it, which are, frankly, staggering.
Oh, the economics are exactly what made me do a double take while reading this.
Right.
The text states that when you switch to this apartment-level system, the cost of a unit of heat drops by 2 times compared to the old centralized systems.
2 times right off the bat.
Yeah, and in some of the more optimized calculations cited in the document, that cost plummets by 5 to 7 times. I mean, I need you to explain how a drop like that is even mathematically possible.
It goes right back to your opening point about heating the dirt.
Ah,
Think about the physical reality of centralized heating. When a giant plant generates heat, it has to forcefully pump thousands of gallons of boiling water through miles of underground, aging steel pipes to reach your living room.
just miles and miles of it under the city.
Right. And no matter how well you insulate those pipes, thermodynamics dictates that a massive percentage of that thermal energy is going to be lost to the freezing earth along the way.
Because it's winter and the ground is freezing cold.
Exactly.
Yeah.
You are burning fuel simply to compensate for transmission loss.
So by generating the heat at the exact point of consumption, literally 3 feet away from your shower or your radiator, you just completely eliminate the transmission loss.
Completely. You burn a fraction of the gas, which cuts down on overall consumption and drastically reduces harmful emissions. It is economically viable, both during the initial construction phase for the developer and over the lifelong operation of the building for you, the resident.
Okay, but let me ask a practical question about how these are installed. If these boilers are so small and efficient, how do the engineers know what size boiler to put in each apartment?
That's a good question.
Because you would logically assume that the square footage of the apartment dictates the power of the machine, right? Like a tiny studio apartment gets a tiny 10 kilowatt unit, and a massive penthouse gets a 30 kilowatt unit.
Yeah, that is the logical assumption. You look at the volume of air in the room and you size the machine to heat that volume of air.
Here's where it gets really interesting, because the document explicitly states that the power of the boiler is actually dictated by something else entirely.
It is.
It has nothing to do with the square footage. It is dictated by your domestic hot water load, the DHW. It is the energy it takes to run your shower, not to heat your living room.
Yes, and the physics behind why that is true is just fascinating. Heating the ambient air in a room is actually a relatively slow, low-intensity process.
Really? Even in winter?
Yeah. Once a room reaches 72 degrees, you are just gently maintaining that temperature, compensating for the slow heat loss through your walls and windows. Air just doesn't require a massive burst of energy to stay warm.
But water does.
Exactly. When you turn on a hot shower, you are demanding an instant, continuous flow of water to be flash heated from, say, 40 degrees Fahrenheit in the winter up to a piping hot 105 degrees in a matter of seconds.
Oh, wow. I never thought about it like that.
Yeah, water is incredibly dense and requires an immense amount of energy to change its temperature that rapidly. That requires an immediate massive spike in thermal energy. So the engineers size the boiler solely to ensure it can handle your hot water demands.
Because if it is powerful enough to handle your morning shower, it inherently has more than enough power to easily keep your radiators warm.
You're exactly right.
It is wild to think my morning shower is the ultimate stress test of my apartment's engineering.
What's fascinating here is how this purely mechanical, physics-based solution completely solves a notorious social problem, which is the thermostat war.
Oh, the thermostat war.
Yeah. With central heating, the municipal plant decides the temperature for the whole district based on an average. The result is that half the building is freezing, so they beg the super to crank up the heat.
And then the other half of the building is boiling, and they have to open their windows in the dead of winter just to survive the heat.
It is incredibly wasteful. Individual heating returns the autonomy entirely to the consumer. You set your exact desired temperature, the system delivers exactly that, and you only pay for what you actually use.
That makes perfect sense for you and me on a personal level.
Yeah.
But if we are looking at this from an urban planning perspective, it brings up a massive structural problem.
How so?
Well, I get how this works for one apartment, but what happens if you are a developer building a massive 300-unit high-rise apartment complex or large commercial facility?
Right.
Running 300 individual, highly combustible gas lines through the walls to 300 individual boilers sounds like an absolute safety nightmare and an architectural headache. You can't just go back to relying on the giant city power plant. So how do you scale this localized efficiency up safely?
You're totally right. Putting individual gas lines in a skyscraper introduces a level of complexity that developers really want to avoid.
Yeah.
So the sources outline a very elegant intermediate solution for this.
Which is?
Block modular boiler houses.
Block modular.
Yeah. Historically, like leading up to the 1990s, these were mostly used for remote or temporary sites. Think of a distant logging camp or a temporary mining operation where you couldn't possibly lay permanent city infrastructure.
Right, out in the middle of nowhere.
Exactly. But today, the technology has advanced so much that they have become incredibly popular in everyday municipal housing and commercial developments.
You know, when I was reading the description of these block modular systems, my mind immediately went to building computers.
Oh, yeah.
Yeah. In the old days, if you wanted a powerful computer, you had to source the motherboard, the fan, and the power supply separately and build it yourself on site, hoping you didn't short a wire. But these modular houses are like buying a high-end pre-assembled machine. They aren't building a traditional brick-and-mortar boiler room from scratch down in a dusty basement.
No, not at all. The construction methodology has entirely changed. They are completely factory assembled.
Like Legos.
Pretty much. The engineers construct the entire boiler system, the boilers, the complex heat exchangers, the water pumps, the electrical panels, and the gas manifolds, all inside an insulated, weatherproof sandwich panel container.
Wow. All of it just inside a shipping container style box.
Yes, and they build it in a controlled, high-quality factory environment where every weld can be inspected perfectly. Then they simply put the entire room on the back of a flatbed truck, drive it to the site, and drop it in the courtyard.
And because it is already a self-contained module, you don't need to pour a massive, expensive concrete foundation or spend 6 months doing site construction. You literally just drop it, plug it into the local gas, water, and electricity networks, and boom, you have a fully functioning, high-capacity utility room.
Precisely. And the way they generate heat inside those modules is highly sophisticated, too. For multi-apartment buildings, the text details how they use a cascade approach.
A cascade approach, meaning what exactly?
Instead of buying one massive, lumbering, multi-ton boiler that takes hours to heat up and cool down, they link together a cascade of small or medium-sized condensing boilers.
Ah, and the text specifically calls out these condensing boilers for having a very small footprint, but incredibly high efficiency. I mean, the regulations state they must have an efficiency rating of at least 0.8. How are they achieving that?
It all comes down to recapturing waste. Traditional boilers vent a lot of exhaust gas out of a chimney, and that gas contains water vapor.
Okay, just steam blowing away.
Right, and that vapor is carrying away valuable heat energy into the sky. Condensing boilers are designed with specialized heat exchangers that actually cool the exhaust gases down enough to condense that water vapor back into liquid.
Oh, wow.
Yeah, and when water turns from a gas back to a liquid, it releases latent heat, which the boiler recaptures and puts back into the heating system. That is how they hit that 0.8 efficiency mark. They're literally squeezing every last drop of thermal energy out of the exhaust.
That is brilliant. They are tiny but mighty.
They really are. If we connect this to the bigger picture, the rise of these modular cascading units perfectly mirrors the economic reality of modern city building.
How so?
Well, in an era where municipal budgets are stretched impossibly thin, the old model of spending 10 years and hundreds of millions of public dollars to lay miles of pipes for a new district just isn't viable anymore.
Oh, I see.
Now, private capital is driving development. A developer can build a new housing complex, drop a block modular unit into the courtyard, and have the entire neighborhood heated efficiently, cleanly, and immediately without waiting on city bureaucrats to update the grid.
Okay, but let's play out an even harder scenario. The block modular system is great if you have a courtyard. But what if you have a dense urban high-rise right in the middle of a crowded city?
Yeah.
Say downtown Tokyo or New York? You need to heat a 40-story building autonomously, but there is absolutely zero extra ground space for a modular container. The basement is already full of parking or electrical equipment. Where does the engineer go when they run out of ground space?
You have only one direction left to go. You point it upward, you go to the roof.
Taking the heat to the sky.
Exactly. Roof-mounted boilers are increasingly one of the most widely applicable solutions for autonomous heating in highly dense environments. They're highly automated, gas-powered units placed either on flat roofs or specially designed pitched roofs.
And they just sit up there.
Yeah, usually housed in light, fireproof metallic structures. The sources note that these are the perfect solution for overloaded existing networks.
Right, because if a city's central heat lacks the capacity to serve a new high-rise, instead of tearing up 3 miles of asphalt to install bigger pipes, you just pop an automated station on the roof of the new building.
Exactly. They can even be designed specifically to handle just the peak loads during a brutal cold snap, stepping in to relieve a struggling central grid when demand is highest.
Wait, let's stop for a second and talk about the reality of this.
Yeah.
With all this heavy machinery, the industrial water pumps, and most importantly, the high-pressure gas lines, Can you really just stick these on top of any bill?
It does sound sketchy at first.
Having a massive gas boiler poised right over my head while I sleep sounds incredibly nerve-wracking. What happens if something goes wrong?
You are not the only one nervous about that, which is why the regulations outlined in the text are intensely, uncompromisingly strict. They are designed entirely around managing the absolute worst-case scenario.
Okay, good.
First, there are hard physical limits on the power. The maximum total capacity for a roof-mounted system cannot exceed 3 megawatts. And within that system, no single boiler can exceed 500 kilowatts.
So they are keeping the potential energy of the system mathematically constrained.
Exactly. They are managing the thermal and pressure limits rigorously. For example, the water temperature is strictly capped. It cannot exceed 95 degrees Celsius.
Why exactly 95 degrees?
Because water boils at 100 degrees Celsius at sea level. If you heat it past that point, it turns to steam.
Right.
And steam expands violently. It takes up roughly 1,600 times the volume of liquid water. Managing steam requires vastly different, much heavier pressure vessels. By strictly capping the system at 95 degrees, they ensure the system remains a hot water system, entirely preventing the physics of a catastrophic steam explosion.
That makes a ton of sense.
Similarly, the pressure maxes out at 1.0 megapascal.
What does 1.0 megapascal look like in the real world?
That's about 145 psi. To put that in perspective, that is roughly the pressure inside a high-end professional racing bicycle tire.
Okay, wow, so it's not crazy high?
No, it is highly pressurized, sure, but it is not industrial power plant pressure. Furthermore, the gas supply itself is heavily regulated. The natural gas pressure allowed directly into the boiler can only be up to 5 kilopascals, which is very low.
But wait, the city gas lines running under the streets operate at much higher pressures than that, don't they?
They do. If the city gas line happens to be low pressure, it hooks right up. But if it's a medium pressure line coming from the city, which can be up to 0.3 megapascals, the engineers are strictly required to install a specialized cabinet gas control point. The text abbreviates this as a year.
Year. What exactly does that do mechanically?
Think of it like the regulator on a scuba tank.
Okay.
The compressed air inside a scuba tank is at a pressure way too high for human lungs to breathe directly. The regulator physically steps down and throttles that pressure so you get a safe, manageable breath. The AIS does the exact same thing for the building.
Oh, I see.
The gas from the city is coming in hot and fast, at a pressure way too high for a roof boiler. This cabinet intercepts it on the exterior of the building, physically steps down the pressure, and ensures it enters the roof station as a gentle, perfectly safe stream.
And I imagine there are automatic shutoffs if that stream stops being gentle.
Absolutely. The inside of the boiler room must be equipped with an automatic safety shutoff valve that is electronically linked to an advanced gas alarm system. At the very first detection of a leak, long before it reaches a combustible mixture, the system kills the fuel supply instantly.
That definitely makes me feel better about the engineering. But still, are there places you absolutely cannot put them, regardless of the fail-safes?
Yes. The text lists strict zoning prohibitions. You cannot place a roof boiler over a school, a kindergarten, or a hospital. You cannot place them directly over residential living spaces, so if they are on an apartment building, they must be situated over a stairwell, an elevator shaft, or a dedicated technical floor. You cannot put them over any storage facility classified as Category A or B for explosive and fire hazards.
Obviously.
And you cannot place them over public spaces designed to hold more than 50 people at once. The engineering itself is incredibly safe, but the zoning rules ensure that if multiple fail-safes were to break down simultaneously, the human risk is statistically minimized.
That makes perfect sense. They are mitigating the human density around the machinery. But looking at all these restrictions, the strict capacity limits on the roof, the tight sizing of the individual apartment boilers, it brings me back to the demand problem.
Okay, the demand problem.
Yeah. If these autonomous systems are heavily capped to stay safe and small, how do they handle those sudden, massive spikes in demand? Imagine a high-rise building where 300 people wake up at 7 a.m. on a freezing Tuesday in January, and they all turn on their hot showers at the exact same time.
A very realistic scenario.
Right. If the system is capped, how does it not just immediately run out of hot water and collapse?
This is where the engineering gets remarkably clever. The system relies on a specific formula logic detailed in the text. When calculating the necessary power for the hot water load, which the formula denotes as cry, the engineers do not calculate based on the absolute maximum possible spike.
They don't?
No. They don't build a machine big enough to heat 300 simultaneous showers indefinitely. They calculate the capacity based on the average hourly consumption over the day of highest water use.
But wait, if they only planned for the average hourly use and a massive concentrated spike hits at 7:00 a.m., wouldn't the water inevitably run cold for half the building? I mean, the math doesn't add up.
It would run cold, and it's not for a brilliant operational mechanism called coupled regulation.
Coupled regulation.
Yes.
Yeah.
When that 7 a.m. shower spike hits, the automated system immediately recognizes that it needs significantly more thermal energy than it normally allocates for domestic water. So it performs a neat trick. It temporarily steals heat away from the building's space heating system.
Wait, what?
It forcefully diverts the thermal power that was meant to keep your radiators warm and pumps 100% of it into the hot water heat exchangers, ensuring that everyone gets a piping hot shower.
Wait, so when the entire building showers, my radiators actively cool down?
Yes, the boiler literally stops sending heat to the radiators.
So what does this all mean? If it's the middle of winter and the heating system literally turns itself off to heat the shower water, won't I freeze? How is my apartment not turning into a freezing icebox while my neighbor showers? Are they somehow cheating the laws of physics here?
Well, no, they aren't cheating physics. They are utilizing it to their advantage. They're using the building itself. The engineers rely on the fact that the physical structure, the concrete walls, the thick floors, the brickwork, acts as a giant thermal battery.
Great thermal battery, explain that.
It relies on a principle called thermal mass. Dense materials like concrete and brick are incredibly good at absorbing joules of heat energy, holding onto it, and then releasing it very, very slowly. Think of a heavy cast iron skillet. You can turn the stove burner completely off, but that skillet is going to stay hot enough to cook an egg for another 10 minutes.
Yeah, that's true.
The building works the exact same way. By the time the system steals the heat for the morning shower rush, the walls of the building have already absorbed so much thermal energy over the course of the night that they continue to slowly radiate heat into the room.
Oh, wow. So the ambient air temperature doesn't drop because the building itself is discharging its stored heat to make up for the radiators turning off.
Exactly. You never even notice the temporary drop in the radiator's power. The building is bridging the gap. Once the shower rush is over, usually within an hour, the system switches back and actively recharges the battery by pumping high heat into the rooms again.
That's amazing.
Alternatively, the text notes, the system can use physical hot water storage tanks to buffer the load, but the principle of coupled regulation using the building's mass is incredibly elegant and requires zero extra equipment.
That is just incredible. To summarize what we've covered in this deep dive, the world of keeping us alive and warm has evolved drastically.
It really has.
We have moved from these blunt, massive, centralized grids pushing heat blindly across miles of frozen ground into highly efficient, smart, and deeply localized systems.
Yeah, it's a huge leap forward.
Whether you are looking at a micro boiler hanging quietly in your kitchen, a plug-and-play modular container dropped into an urban courtyard, or a high-tech, heavily regulated station sitting safely on a roof, the technology has adapted to be exactly where we need it. It is literally using the very walls of our buildings to store energy, balancing our needs second by second.
This raises an important question for anyone living in a modern city, honestly. How much invisible, highly calibrated engineering is constantly adapting to our daily unconscious habits?
Right.
Every time you turn a shower handle, an entire localized ecosystem instantly calculates that demand and responds to it, shifting resources silently in the background.
It really leaves you with something to think about. If our buildings are becoming this autonomous and this smart at managing their own localized heat, I mean, literally storing thermal energy in their own walls, diverting resources precisely where they are needed, and generating power exactly where it is consumed, are we moving toward a future where our buildings act less like inanimate brick structures and more like living organisms with their own self-regulating metabolisms? From the cafeteria line to the personal chef, and now to a building that breathes, adapts, and reacts to us. It fundamentally changes how you look at the walls around you.